Hey everybody. So today I wanted to go through that number 5 on the Coulombs law of field problems worksheet. There's a number of people that are going to be out today due to various AP tests, and I wanted to make sure that you saw this. It's a great opportunity to look at vector addition and the fact that when we look at electric fields, we have to take into account all of the electric fields that are acting on a certain point in space. So if you could, find that worksheet. It's right here, Coulombs law of field problems. I believe in class we would have gotten through numbers 1 through 4 the other day. And if you could, take a moment and flip that paper over to the back. So there should already be a picture drawn. And what it asks for is, what is the electric field at X? Now it's given two charges, a plus 2 microcoulomb and a minus 5 microcoulomb, and they're 4 meters per side of the square. And what we're really looking for is, what is the electric field right here? Now, before I begin, I gotta recognize a few things. The electric field caused by a positive charge is always going to point away. But you know what? I don't care about the electric field at other points in space. In fact, I only care about the electric field at X in this problem. So what I'm gonna need to do is I'm going to actually have to draw in that electric field as pointing away from the 2 Coulomb charge. So E2. Now, for the negative 5 charge, we know that electric field lines point towards the negative charge. So field lines pointing in all directions. But again, we don't care. What we care about is the electric field line at X. So that if something were placed there, it would experience a force. Now, that electric field line is going to point straight down and be equal to E5. I now have 2 vectors, tail to tail, that I can use. I can solve for the electric field from each one, add them together as a vector, and here we go. So how do we find the electric field? Well, the electric field for a point charge, we can solve for using KQ over R squared. And the numbers here are pretty easy. We've got 9 times 10 to the 9th. Q is going to be 2 times 10 to the minus 6. And the distance from the plus 2 charge over 2 point X is going to be 4 meters, so 4 squared. So go ahead and punch that into your calculator. You got it. Yeah, nice job. You get 1,125, and it's newtons per coulomb. Now, because it's a vector, I'm also going to throw in that it's pointing to the right. So I just found the electric field caused by the plus 2 microcoulomb charge. All right? Hey, this is easy stuff. Nice. Bask in the easiness. That's okay. So to find the electric field from 5, I'm going to follow the same procedure. Now notice, when I plug in my numbers, I'm not going to plug in the sign on the charge. It's going to be 9 times 10 to the 9th, and then just 5 times 10 to the minus 6. The negative sign we take into account when we're showing that it's pointing down. We're going to look at it as a vector. And I take that divided by, happens to be the same distance, 4 squared. So if I find E5, and unfortunately I don't remember the answer to this one, 2,812.5. Or because I'm going to round a little bit here and there, maybe I'll call that 2,813 newtons per coulomb down. Hey, we're almost done. No, not quite. So what we're really doing here, when we take these 2 vectors, remember this is my opportunity to review vector addition. So for vector addition, you know that if we have 2 vectors, we've got to put them tip to tail. So I'm going to start off with my E2 vector that's pointing, well, first I got a start spot here, a starting point. Point to the right with a magnitude of 1,125 newtons per coulomb. Then I'm going to take that electric field from the -5 charge and add it tip to tail. Oh yeah, that's not so bad. So then to add them, I go from the beginning to the end. And I start my vector, and here it goes. That is the resulting vector. I'll just label it as E. Try that again. Now what's really nice here is that I've got two vectors, one in the X and one in the Y direction. So bam, by definition, they're going to be at 90 degrees to each other. So easy. So all I have to do is use the Pythagorean theorem. So I've got E squared equals 2813 squared plus 1125 squared. Plug it in, take the square root. I've got 3029. Now, should I round that to 3030? Yeah, probably. But I know I think I might just leave it at that. Hey, I'm done. Oh, no, wait. It's a vector. And since it's a vector, this is solely the magnitude of the electric field. And because it's a vector, I need to know the direction. So to find the direction, I got one last step. Any suggestions? Yeah, that's a good call. Nice. Yeah, it's a right triangle. Let's label this angle theta. And I can just use my right angle trig. Oh, gosh. Yeah, you guys have learned a lot this year. I think the trig function I would use in this case is going to be the tangent of theta equals opposite over adjacent. So I take the inverse tangent. Now, a lot of you guys are in pre-calc. A lot of you in calculus. You know you've got to take your calculator and convert it back into degrees. So you do that with document settings. I'm hoping you know how to do that by now. So go ahead and punch that in. Yeah. Did you get 42.8? Oh, good. I'm glad, because that's wrong. Did you get 68.2? Yeah, that's right. Good. Now, hey, we're 68.2. Point. Point which way is 68.2 degrees? Where is it? It's about there, right? Is that what my arrow looks like? Nope. Oh, shoot. My 68.2 is my reference angle. I can't leave that as my final answer. That looks stupid. You know what I need to do? I need to put that angle in the coordinate plane. So in the coordinate plane, oh, that's that thing, the 0, 360. Let me get a better pen here. You guys know from calculus that we've got, or pre-calc, 0, 90, 180, 270, 360. And a simple mnemonic to remember which trig function is positive in which quadrant is all suckers take calculus. Yeah, they don't like that one, but I do. I think that one's good. Now, that doesn't have anything to do with what we're doing here. 68.2 degrees, let's take a look at it. If 68.2 is down in this direction, to put it into the coordinate plane, I need to do to find, I'll just call it angle. Yeah, you're right. Nice call. 360 minus 68.2 degrees. That's going to be equal to 292-ish degrees, depending on your rounding. Yeah, 292. So, given that, my final answer is going to be that the electric field is equal to 3,029 newtons per coulomb at 292 degrees. And that is a perfect opportunity for us to review vector addition prior to the AP exam. There you go. I think you got this. Thanks for checking in. Hopefully, if you have any questions, write them down, let me know. Thanks.